In this lecture, we will learn how to apply one-way ANOVA, two-way balanced ANOVA and two-way unbalanced ANOVA, which is nothing but general linear model, and interpret the results. This lecture will spill over to 3 more lectures. Let's start with a scenario. The cycle time for a process is captured for 3 different ways of executing that process. So 3 different sequences. The process designer feels that sequence 1 is better option, and for him shorter cycle time is the main consideration. We want to statistically validate if his assumption is true. So this is a scenario where we have one y and the y is continuous, and we have one x which is nothing but the sequence, and there are 3 levels for that sequence. So we have sequence 1, 2 and 3. So this is an ideal case for a one-way ANOVA. Let's go to Minitab and find out how to perform a one-way ANOVA. Here we are in Minitab and we have the data of all the 3 sequences included here. So we have sequence 1, 2 and 3. As a prerequisite, we have to go and find out if our data is normal. So I could go and perform the Anderson-Darling normality test here for all the 3 data points separately, or I could go and click on graphical summary, which is what I'm going to do, and I'm going to select the 3 sequences, and at one go I might be able to produce 3 different graphs. This is the 3rd sequence, and my Anderson-Darling test is part of the graphical summary here, and the p-value is greater than 0.05 for the 3rd sequence. For the 2nd sequence as well, it is greater than 0.05, and likewise for the 1st sequence also it is greater than 0.05. So all the 3 sequences, meaning all the data that I have, are normal. That is a confirmation that one of the prerequisites has been met. Now the other prerequisite that I need to check for is equal variance. So I go to Start, I go to ANOVA, and right somewhere near the bottom I have a test called as Test for Equal Variance. I click on this and it tells me that there are 2 ways in which you can enter the data. One is when you have the data stacked, and the other is when we have the data in different columns. In our case, we have the data in different columns. So I'm going to select the 2nd option and I'm going to click on the 3 columns like I did with graphical summary, and I'm not really worried about anything else because this is nothing but another hypothesis test, and this test is performed to find out if the variance of sequence 1 is equal to the variance of sequence 2 is equal to the variance of sequence 3. So that becomes the null hypothesis. I'm going to click on OK, and Minitab here produces p-values. It has the p-value for what we call as a Levin's test, and the p-value here is greater than 0.05. And clearly you would see that the confidence interval for the variances are overlapping, and that is why the p-value is also greater than 0.05. That confirms to us that the variance of these 3 samples are equal. So with that confirmation, I'm going to go back and perform the one-way ANOVA. So go back to Stat again, go to ANOVA, click on one-way. The moment I click on one-way, there are 2 options again here. One option is for me to select stacked data. That is, if I have all the responses and the factors in different columns, I could use this option. But for us, we're going to use the other option where we have sequences in different columns. So I'm going to click on sequence 1, 2 and 3. I'm going to come to options. In options, I'm going to check this because I have tested for equal variance. I'm going to click on this. If I don't click on this, Minitab will still run an ANOVA, but it will do what is called as a Welch test, and it won't do a proper ANOVA. We're not worried about that right now. We'll click on this. 95% confidence. I'm not going to change that. 2-sided test. I'm not going to change. Graphs. I'm going to click on box plots and not on interval plots. I'm going to say OK. And then I'm going to come to the results. In results, I'm more interested in the ANOVA. I'm not interested in model summary and means. We'll cover these when we're going to talk about regression. Minitab does a little bit of modeling, etc. also in one-way ANOVA, which we are not really interested. So I'm going to click only on the 3 here and then say OK. And then finally OK again. So I have the box plots and I find that the boxes are overlapping. There is no doubt about it. But the mean of the first sequence is certainly less than the other sequence. So in one way or the other, the assumption of our process designer seems to be true. But unless I don't look at the p-value, I cannot statistically confirm this. So I'm going to go to my session screen and we have the one-way ANOVA here. This is all some basic information about what method of test was used and what was our null and alternate hypothesis. Here is some information about what factors have been included in the study. I'm going to come to the analysis of variance table, which is more important to me. If you recollect, this table is something very similar to what we covered when we talked about the ANOVA table in the theory. So we have the between variation, which is the factor, and this is the total variation. What Minitab calls as error, or in other words noise, is the within variation. We have 3 levels for the given factor, so our degrees of freedom is 3 minus 1. We have 30 data points all put together, so 30 minus 1 is 29, which is the degrees of freedom here, and 27 is nothing but 29 minus 2. I have here the sum of squares. Minitab sometimes uses the term called as adjusted sum of squares, or sometimes it uses what is called as sequential sum of squares. At this point, this is not very important to you. In our two-way analysis, I will talk a bit more about adjusted and sequential sum of squares. This is the mean square. So the mean square is nothing but sum of squares divided by the degrees of freedom. And then the F value is nothing but the ratio of the adjusted mean square for the factor, that is the between variation, divided by the mean square for the error, nothing but the within variation. The F value seems to be very less, which means that the within variation is much higher than the between variation. And that is why Minitab is telling us that the p-value is greater than 0.05, which means it cannot conclude that any one of the sequence is better than the other. The hypothesis of the process design engineer that sequence 1 is better than the other 2 sequences is not necessarily true, because we have taken the whole data holistically and we have performed a statistical analysis. If he had not done that, I'm sure you would be able to forecast what he would have done. He would have chosen, or he would have been banking on sequence 1, which may or may not be different from the other 2. So that is how a one-way ANOVA is performed. Quickly, before we go, I'm going to click on this again, go to my options, and I'm going to now check off assume equal variance. Let's say that the variance were not equal, but I still want to go and perform an ANOVA. So I have checked off the assume variance scenario, click OK and OK again. So now Minitab does the box plot. I'm not interested, but what it does is here it does what is called as a Welch test. In the case of a Welch test, you won't get the ANOVA table, but you would get the p-value alone. And the p-value is not any different from the p-value that we got with the ANOVA here. The values are nearly same, but it is a different test, which is used when the variances are not equal, or we don't know whether the variances are equal. So with that, I'm going to wrap up this lecture. In the next lecture, we will talk about two-way balanced ANOVA. Thank you.